Hello, hello, hello everyone. Today we shall discuss about mechanical properties of matter. You see, this is the visible strength, invisible science. Understanding the mechanical properties of the world around us. You see that how do we build things that don't break? Why the railway tracks and structural beams shaped like an eye? You see here, this one. Why? The question is why? This is the tension, this is the neutral axis, this is compression. How can we design an airplane that is both incredibly light and immensely strong? A strong composite skin, a strong composite skin you see here, and lightweight honeycomb core. This is the composite metals. This is traditional metals, strength to weight ratio. The illusion of rigidity. In history, the illusion of rigidity is the illusion of rigidity. This is what we call it as elasticity, and this is plasticity. The property of a body to regain its original size and shape when an applied force is removed. And that property is known as elasticity. And what is plasticity? The property of a body to be permanently deformed by a force. For example, think of putty. The behavior is a key to engineering design. The internal battle, understanding stress. When external force deforms a body, an internal restoring force develops. The stress is this restoring force per unit area. Tensile and compressive stress, forces pulling or pushing perpendicular to the surface. You see here, this one is perpendicular. These forces are perpendicular to the surface. Stress, that is sigma, can be written as force by area. The SI unit is the Pascal. This is tensile and compressive stress. Here you see here, forces pulling or pushing perpendicular to the surface. In this case, shearing stress, forces acting parallel to the surface. And hydraulic stress, uniform pressure on all sides, uniform pressure on all sides like a sphere in a fluid. The physical response, measuring strain. Strain is the measure of deformation. The fractional change in a body's dimension, it has no units. Longitudinal strain, the cylinder gets longer or shorter, del L by L. This is longitudinal strain. The cylinder gets longer or shorter. Del L, del L means change in length and L means original length. Strain is a measure of deformation. The fractional change in a body's dimension, it has no units. Shearing strain, the cylinder faces The cylinder faces displace relative to each other. That is del x by L. Del x by L, that is the shearing strain. And volume strain is the sphere's volume decreases. Change in V by original V. Or change in del V by V. That is the volume strain. So we have longitudinal strain, shearing strain, and volume strain. In longitudinal strain, we get del L by L change in length by original length. In shearing stress, we get the cylinder's faces displace relative to each other, del x by L. And in case of volume strain, we get the sphere's volume decreases, del V by V. The next one is law of proportions. You see, for all deformations, stress is directly proportional to strain, and this is what is Hooke's law. You see the weight 1, 2, 3, 4, 5 centimeter extension or deformation, weight force in kg, and this is known as Hooke's law. What is that? That for small deformation, stress is directly proportional to strain. That is, stress is equal to K into strain, where K is the modulus of elasticity. This modulus K is a fundamental property of a material, its signature stiffness. The story of a material under load. Every material has a breaking point. This curve tells us its life story. This is stress, this is strain, and you see this is the curve A, B, C, A, B, D, and E. This is the curve with the stress and strain. You see, and there is a breaking point also. You can find in chapter 1. The elastic region O to A. You see here O to A, the elastic region. Stress is directly proportional to strain. Hooke's law is obeyed in from O to A. The material behaves like a perfect spring. It returns to its original dimension when the load is removed. This is elastic deformation. Chapter 2. The point of no return A to B. What we call it as the yield point or elastic limit. Stress and strain are no longer proportional. The material still returns to its original state if the load is removed. Point B is the yield point or elastic limit. The stress at this point is the yield strength sigma y. This is the elastic limit. Exceeding this limit means permanent change. Whenever we exceed this yield limit or elastic limit, there is a permanent change here you can find. Chapter 3, permanent set and failure, elastic deformation. Beyond the yield point, you see at the beyond the yield point, the material is permanently deformed. The permanent set, what you call it. Ultimate tensile strength D. The maximum stress the material can withstand up to D, that is this point, ultimate tensile strength D. Fracture E, the point where the material breaks is the fracture. E point is the fracture point. And you see ductile and brittle. If D and E are far apart, the material is ductile like steel. If they are close, it is brittle like glass. You know that glass is a brittle and steel is ductile. A material's personality, the elastic moduli. The ratio of strain to strain in the elastic region gives us a precise measure of a material's stiffness. We have three key types: Young's modulus, shear modulus, and bulk modulus. Resistance to change in length, tensile stress by longitudinal strain, that is known as this one, Young's modulus. Shear modulus or G, resistance to change in shape, sharing stress by sharing strain. Bulk modulus, resistance to change in volume, hydraulic stress by volume strain. Resistance to change in volume, that is hydraulic stress by volume strain. This is a bulk modulus. Resistance to change in volume, hydraulic stress by volume strain. Why steel is not rubber? There is question that why steel is not rubber. To increase the length of a thin steel where by 0.1% a force of 2000 Newton is required. The force required to produce the same strain in aluminum is 690 Newton. A large Young's modulus means a material is very stiff and requires immense force to produce a small deformation. This is why steel is preferred for structural design. See the Young's modulus. This is stiffness steel, this is bone, this is wood, this is the stiffness of steel, or we call it as Young's modulus. How much can a 1 centimeter steel rope lift? Here you see the problem is a crane must lift 10 tons, 10,000 kg. How thick must its steel rope be to avoid permanent deformation? The science, the stress in the rope must not exceed the yield strength of steel. For data tables, sigma y for mild steel is 300 × 10⁶ Newton per meter square. The calculation, force weight on 10,000 kg into 9.8 and 8,000 Newton. Required area, force per sigma y. Therefore, it is getting as 3.3 × 10⁻⁴ meters square. The answer, this corresponds to a radius of about 1 centimeter. A safety factor of 10 is usually added, recommending a 3 centimeter radius rope. This way you can find how much can a 1 centimeter steel rope lift by the process of Young's modulus. Now we learn another thing, why the I in I-beam. The equation of bending, this is the equation of bending, we get the equation of bending here. The equation of bending, sag del is proportional to W L cube by 4B D cube Y. W is the load, L is the length, B is the breadth, D is the depth, and Y is the Young's modulus. In sight, bending is proportional to 1 by B breadth, but is proportional to 1 by D cube, that is depth. Increasing depth is far more effective at preventing bending than increasing breadth. The solution, the I-beam shape. The I-beam shape maximizes depth while removing a non-essential material from the middle, reducing weight and cost without sacrificing strength. The limit of a mountain, you see what is the main thing in mechanical properties of matter. The limit of a mountain. The question, why can't mountains on earth grow infinitely tall? What is the reason for that? is science. The base of a mountain is under immense pressure from the weight above it. This creates a shear stress within the rock. If this stress exceeds the rock's elastic limit, the rock will flow like a very slow liquid fluid. The calculation you can find here that stress at base h into rho into g, height into density into gravity. Elastic limit of typical rock 30 into 10 to 7 Newton per meter square. Solving for h gives h equal to 10 kilometer. The height of Mount Everest is very close to the theoretical maximum for a mountain on earth. From the tallest mountain to the strongest steel, our world is shaped by the invisible laws of stress and strain. Dear friends, if you like this video, please subscribe, like and share. Thank you everybody for watching this video.